Good morning, everyone. Welcome to SciFiDevCon. My name is Alon Miroinik, and I work for Black Duck, where I manage the R&D for the Seeker agents. Seeker is our IAST tool, Interactive Application Security Testing tool, and frankly is probably the best IAST tool out in the market today. But as fascinating as application security is in general and IaaS is in particular, it's just not my topic today. So this is the last time I'm going to mention Seeker. Today I want to talk about something a bit different. So like every year came round, I of course wanted to participate in SciFiDevCon, and I wanted to talk about something that I knew about, something I was working on, something that was kind of on the top of my mind. I wanted to talk about mutation testing. But of course, I wanted to give it some superhero flair and make it on topic for this conference. Have to admit, if you hear about mutation testing, the way you spin this to science fiction or to comic books or superheroes is kind of obvious. But I just couldn't make this work. I could not put an idea together that worked for me. So I tried thinking about the other obvious way to go with mutation. And I couldn't get that to work either. So I had to take a step back, I had to think for a moment, and then I understood that if you're talking about mutation testing, the interesting part probably isn't the mutations themselves. I wanted to talk about what we want to achieve here and not how, which is the mutations. So what we want to achieve here, if we're quoting Alan Moore, is to watch the Watchmen. When we write code, we quite often write tests for it. Specifically, I'm going to discuss unit tests, but the general concept applies to any type of testing you can be doing. And the reason we write tests is because we want them to be our superheroes. We want them to protect us. We want them to watch over us. We want them to keep us safe when we modify the code, when we write new functionality, when we try to fix bugs. And to the most part, unit tests do indeed do this for us. But herein lies the dilemma. Who watches the Watchmen? How do we know that our tests that we run religiously in our CI/CD pipelines and make sure we always get a nice green tick from them, how do we know they're actually watching over us? How do we know they don't just pass and not protect us? This is what my presentation today is about, and we will shortly see how mutation testing fits in here. But let's start with some basics. In the previous slide, if you were paying attention, you may have noticed the word Python. So all my examples today will be in Python, but I won't be using any fancy syntax. I won't be using anything that's too out there. I'm using Python because recently I've been working with Python, but I want you to not focus about the syntax or the specifics, but on the concepts I'm going to share here. So let's get started. Let's get started with some code. So we go to our team of so-called superheroes and we ask them, please write a sorting function for us, which they happily do. And now, since we want to make sure this function is correct, we write a unit test for it. Very simple. We have some data. We take the sorting function that we got, QD sort, which of course stands for quick and dirty sort, and use that to sort our data. We use the built-in sorted function to sort the data. We compare them and we assert that they are equal, proving that this QD sort works just like the built-in sorted function. Great. How do we know we can trust this test to actually protect us? How do we know that this test really proves that the QD sort function indeed sorts correctly? Well, first of all, a very common way of doing this is using coverage. So coverage essentially runs our test and reports back which statements, which branches, which control flows of the production code, of the code that we're testing, the test actually covered. So over here, I'm using a Python tool called coverage. We use this to run our tests. We then generate a report, and we can see that we've covered 100% of the code, which sounds great. We have a perfect test. It covers all the code. Well, not exactly. What if out of all the Watchmen, the comedian wrote our sorting function, and this is its implementation, just to return the list as is? We are indeed covered, but maybe the test it isn't great. Maybe the fact that we covered 100% of the code isn't enough to say we covered 100% of the functionality. So let's try and make our test a bit better. We'll add a test case. Now we're testing this QD sort function on two inputs, on 123 and on 132. And if we run our tests now, we can see that they actually fail. This so-called sorting function fails to correctly sort the list of 132. So back to the drawing table, let's fire the comedian, let's get someone a bit smarter or at least a bit more serious to write our sorting function. We'll ask Night Owl to help us and write an actual sorting function. This, of course, is a quicksort implementation, but use whatever sorting algorithm you see fit. And now, if we run our tests and our coverage, we see that indeed the tests pass and we cover 100% of our code. But again, this may not be good enough. Covering 100% of the code does not mean our code is bug-free. Coverage is great, but it's a very limited tool. We need to use it for what it can do and not assume it does anything that it's not designed to do, which sounds a bit like tautology, but let me explain. We can say with an absolute degree of certainty that if a path in the code is not covered, we do not test it. This is not always a huge problem. It can definitely help us identify gaps in our testing. It can help us identify where we're missing test coverage. But in the real world, this isn't always the end of the world. Quite often, you'll see really good test suites that don't cover exception handling. In Python, not so much. In languages that are stricter with their exception handling, you'll see this a lot, like in Java, where the syntax kind of forces you to have a catch block somewhere, but in the real world, this isn't an interesting problem. You have a code that you know runs internally, fetches a resource from an HTTPS endpoint, and the language kind of forces you to handle an exception of what if the certificate on the other side isn't trusted. So you'll have a catch block and you'll bail out, but to be honest, it's not a very interesting flow to test, and in the real world, it won't really happen. And also, more than not interesting, it's pointless. If you can't fetch this resource, none of your program can work, so it should just bail out and exit. There's not really a good use case to write a unit test here. What are you going to test? That your error message is legible enough? You test this once manually, you see you like the error message, and that's about it. Can you invest a huge amount of time to mock everything up and capture the output and test it? You can. Will you? Realistically, no. So even if your code isn't 100% covered, sometimes it's okay, but you need to be intentional about it. Don't just say, okay, I write my test and I don't care, but go over the coverage report, see what you aren't covering, and decide explicitly, okay, here's a gap, I want to test this, or this isn't an interesting flow, I'm not going to bother, or yes, it's interesting, but it's a huge amount of work, let's schedule it for some time later. Be intentional about your testing. But that's kind of a side point, a tangent. What we've seen here, that even if we do cover 100% of the code, it doesn't necessarily mean we covered 100% of the bugs. So again, coverage is a very limited tool. It will tell you your test code caused the production code to execute these and those statements or these and those blocks. Were they executed correctly? Does the output they produce make any sense? That's a bit too much to expect from coverage to handle. Just as you've been here. If you execute every single line of code in every control structure in your program, you will have 100% coverage. But you could, for example, have a test with no assertions, which would not be very useful. It won't prove anything is actually executed correctly. It will just prove that at best it executes without crashing horribly. So coverage is important. It should be used, but let's not build mountains of expectations on it. Now, let's go back to the reason I really wanted to have this talk and see something a bit fancier that might actually help us track down bugs. Introducing mutation testing. So what mutation testing does in a nutshell is it tests how strict your tests are. What it does is it takes your code and introduces mutations. So it deliberately changes parts of the code and then runs the same test suite on them with the expectation that it will fail. Because if our code started out as being correct and we changed it, we have now introduced a bug. whenever this test suite fails with a mutation, that's great. It means we caught it. We're able to identify a bug being introduced at that point. Wherever we didn't, and we see this over here with the sad smiley emoji, we know our test suite may be lacking. There is a point where we were able to change the code. We supposedly introduced a bug, and our test suite failed to catch this. So, what do we see here? I'm using a tool for Python called mutmut or mutmut. I'm actually not sure how this is pronounced, but we run it. There's some very basic configuration here to tell it how to run my test suite. It generates mutations in the code, as I said. We have here 17 different mutations. 14 of them were properly caught. 3 of them the test failed to catch. So we can now ask mutmut for our results, see what mutations have survived. For argument's sake, let's look at mutation number 3. So we can ask mutmut to show it. We get a very nice patch output here that shows that in our code, excuse me, if we change the condition here to if n is less or equal to 1 to if n is less than or equal to 2, our test suite failed to catch this. So now that we know that we have a dangerous mutation that introduced a bug, what will we do with that? So, like any process of improving our testing, we'll first introduce this bug. So we can ask mutmut to do this for us, just mutmut apply the mutation. We run our tests, and we know they'll pass, but we'll run them manually just to be sure. And now we go back to our tests. This is the only part of the process that isn't automated. And now we have to do the hard part and think. We need to find a test case that will fail with this mutation. Now, since the use case here was if a list has one or less elements, just assume it's sorted and return it, and we changed it to 2 elements and it failed. Well, let's just introduce a list with 2 elements, the list of 2, 1. And now if we run the test, it indeed fails, which again is a good thing. We intentionally damaged our code. We intentionally introduced a bug. So we want our test to fail. We want to make sure that a test will catch this bug. Now that we have, we can of course remove the mutation. We can run the test again, make sure it now passes, commit this change if we want to. And now we run mutmut again, and we can see we only have 2 mutations now. So if we look at 2 and 5, mutation number 3 that we already handled no longer exists here. You'll see the mutations are consistent, which is kind of nice because we had a really small number of changes. In fact, we had no changes to the production code, so the mutations will be exactly the same. But let's look at them and let's see if we can handle them. So mutation number 2, funnily enough, does not affect functionality. It only affects the performance of the code. So, quick refresher, how does quicksort work? We choose a pivot element somewhere in the array. We'll discuss this in a second. And now all the elements that are smaller than this pivot element, we put to the left. All the elements that are larger than the pivot element, we put to the right. And in this implementation, all the elements that are equal to the pivot element, we put in the middle. For each of these parts, or at least for the right and the left, we continue to do this recursively. So then each one of these recursively gets sorted, and then we can merge all of these to one big list that will be sorted. When does the recursion stop? So in our original implementation, when when a list has one element, because by definition it's sorted. With this mutation, we stop when a list is empty. So instead of recursively cutting down the list and getting to one element, we add another stage where we say our single element of the list is our pivot item. Everything smaller to it, an empty list, goes to the left. Anything larger than it, again, an empty list, goes to the right. And then we recursively sort all of these, and both of these, excuse me, both of them are empty, so we're done. This isn't wrong. It's just a redundant step. Mutation testing does not do a great job with mutations that do not affect functionality. So we could try and build a test that is really really sensitive to the performance here, but in the real world, it's probably a bad idea. The other mutation, mutation 5, is again a similar issue. It's also around performance. In the original implementation, our pivot element is the element in the middle of the list, or the element whose index is half of the size of the list. And with the mutation, we move it and say the pivot element is the element whose index is a third of the length of the list. Is this a weaker implementation? Yes. This means our two sides of the pivot aren't equal or aren't even roughly equal. And we'll put probably quite a few more steps of recursion into the longer part. Ultimately, functionality-wise, does this matter? It doesn't. As long as you pivot somewhere, as long as you have, as long as you're consistently able to pivot, it doesn't really matter. You broke up the list somehow into pivot elements, everything that's smaller, everything that's larger. You can keep on doing this until you cut both sides down to a single element and you're done. Taking the mid part is probably the most performant option. Realistically, I could have hard-coded always pivot around element number 2 here, or the second element, the element with index number 1, and it will still work. So again, maybe we can figure out a test that's very conscious on performance and try to kill this mutation. In the real world, I wouldn't bother. What I would do is just ignore it. We can control matmat with comments, with pragmas. So on the pivot element, we just won't care to mutate it. Around the end condition, this one is a bit trickier because we did see we had a mutation there that we did not catch. Matmat, unfortunately, right now does not have the functionality to ignore only specific mutations. I'd love to have the option to not mutate less equal to less than, but yes to mutate the literal 1 to a literal 2. Right now, this isn't an option in matmat. There's a upstream discussion on this, but it doesn't exist yet. So we'll just have to live with this and know that we're explicitly and intentionally ignoring this mutation. But I don't want to dig too deep into this because, again, this isn't a very advanced talk on matmat. It's a talk to introduce the concept of mutation testing. And whatever tool you use, get to know how to configure it, get to know how to exclude stuff. Just read the docs, honestly. Before I wrap this up, just to answer a question that I get asked a lot, in the world of Gen AI, where we have code generated for us and tests generated for us, does this really matter? And the answer is full-heartedly yes. Actually, the QD sort implementation that I shared here, I just asked GitHub Copilot to implement for me. And luckily, it didn't have any bugs, at least no bugs that I could spot, because let's be honest, sorting is kind of straightforward nowadays. Gen AI is great for generating code, it's great for generating boilerplate code, but unfortunately, once you kind of veer out of the realm of boilerplate, you need to be really careful because bugs do happen. And what a lot of people like to do nowadays is to use Gen AI to generate the unit tests, because a lot of the time, and personally I disagree with this assertion, but unit tests are perceived as something boring and boilerplate to write. So now you have generated code, which is watched by generated tests, and you kind of are lacking feedback to say how good these tests are. And even though these tests pass, it's really hard to be sure that these tests are any good and that you can really trust them. And if you can't trust your tests, you cannot trust your code. So full-heartedly, yes. I would actually say, especially for generated tests, watch the Watchmen. Run coverage on them, see what they miss. Run mutation tests on them, see what they don't test well, and either improve them or ask your Gen AI to improve them. And with that, I do want to wrap up. I will leave you with some links both to the code examples that are available on my GitHub and to the tools that I've used, coverage and matmat. So the documentation, the GitHub projects, get involved, get to use them, play around with them. I guarantee it will make your tests better. If any of this resonated with you, sounded interesting, by all means, don't be a stranger. Reach out to me. I'm not a hard person to find. I have email, I'm on X, I'm on LinkedIn. Reach out. Let's keep this conversation alive. And with that, the only thing left for me to do is to say thank you. Thank you for taking time to listen to me. Thank you for attending, and have a great rest of the conference.